Hello, my name is David Hurd, and this is Lab 1 Charge Tapes. First things first, we're going to start with Newton's second law, also known as the momentum principle, which helps you calculate change in momentum and, in our case, force, due to mass and acceleration, which will come in handy when we have to calculate gravity. Next is Coulomb's law, which is very similar to the force due to gravity, and is laid out here and is how you get the electric force. Coulomb's constant is below 9 times 10 to the 9th Newton meters squared per Coulomb squared. In this lab, we will see that one tape will always become positive and the other becomes negative due to the conservation of charge. And when two of the same type get close, they bend away from each other while opposite ones get closer. A charge and a neutral will also get closer. The purpose of this lab is to analyze and understand the charges on pieces of tape and be able to calculate the amount of excess charge on them. And our initial conditions was that the pieces of tape were 0.221 meters in length and had a mass of about 0.221 grams. We also have our constants like acceleration due to gravity, 9.8, and the Coulomb's constant, which I stated before. In this experiment, we had two pieces of tape. One, we would rip off of a base tape, and another, it would either be the base tape or another U-tape in this case. The surroundings were everything else. In this experiment, we did a number of different things, such as holding the pieces of tape to neutral objects like a hand or a pen, in which case they would attract. We would then hold them to other U-tapes that were ripped off and notice that they repelled, meaning they were the same charge. We also showed that they attracted to the base tape, which was positively or oppositely charged. As part of the experiment, we had one piece of tape float above another piece of tape that we assume were the same charge. Using that information, we were able to, and the distance between them being 0.0273 meters, we were able to calculate that the magnitude of the gravitational force on the top tape was 0.0217, and the electric force had to be the same because it was in equilibrium. Here's an example of some of the code where we simulated two point charges with the same mass. Now, the problem with this is that there were assumptions made. In the code, we treated the entire length of the tape as a single point charge, and we assumed that they had identical charges, which wouldn't necessarily be the case because they were ripped off separately. We also assumed air resistance is negligible. Now, after doing the calculations, you find that the charge on one tape would have to be 1.34 times 10 to the negative 8 coulombs in order to repel with the same force as gravity. Now, there was likely some error, mostly due to human part, but there was also humidity, which made the charges really difficult to see and appear naturally. The charges would also be dispersed whenever you touch them, and the measurements could have just simply been inaccurate. Now, what if we switch the signs? So any protons are now negatively charged and any electrons are now positively charged. We would find pretty much the exact same results because opposites would still repel opposites. Opposites would still attract opposites, my apologies. The same charges would still repel each other, and a charge would still repel or still attract to a neutral object. So all it would do is change the sign of some of the charges and forces. Now, why do we have to be careful handling the tape? We have to be careful handling the tape simply because the more you touch it, and the more it touches objects, the more charges are either dispersed or added that we didn't account for, and that is one of our major sources of error.